Okay, so we all think we know Newton's laws of motion, right? I mean, they're the bedrock of physics, the stuff we all learned back in high school. But what if I told you that for almost 300 years, we've been getting the very first law wrong? Yeah, there's a hidden story here, and we're about to uncover it. We're going to start with the one law everyone feels like they know inside and out, the first law of motion, the law of inertia. But it turns out a single critical word was lost in translation, and it completely changes what we thought the law actually means. So just take a second and think back. What's the version that you remember from your old physics class? It probably sounds a little something like this, right? An object just keeps on doing its thing, unless some force comes along to mess with it. This is the definition that's been drilled into our heads for centuries. And it seems pretty straightforward, but it actually creates a little bit of a puzzle. And here's the puzzle. I mean, think about it. When is an object ever truly free of external forces? In our universe, you've got gravity, you've got friction, they're literally everywhere. This is where the whole mystery starts. The key, it turns out, wasn't in the physics, but in the language itself. The whole thing comes down to Newton's original Latin. See, he wrote the word quatinus, which for centuries was translated as unless, but that's not quite right. A better translation is insofar as. Now, this might sound like splitting hairs, but it's a world of difference. Unless talks about some imaginary, hypothetical world with no forces at all, but insofar as describes our world perfectly. It's saying that forces are precisely the reason for any change in motion. It's not about what happens when forces are gone, it's about what happens because they are here. So, if the first law isn't just about some imaginary object floating in empty space, then what's its real job? I mean, why did Newton even bother writing it down in the first place? Well, a really common critique you hear is that the first law is just kind of a redundant part of the second law. If F equals ma, then it makes sense that when the force, F, is zero, the acceleration, a, also has to be zero. And zero acceleration just means constant velocity. So why state it separately? Because the first law isn't actually describing motion at all. It's setting the stage. Its true purpose, its whole reason for being, is to define something called an inertial frame of reference. Think of it as the neutral ground, the specific non-accelerating point of view from which the second law, F equals ma, actually works the way it's supposed to. Without the first law defining the rules of the game, the second law is basically useless. Here's a great way to picture it. Let's say Alice is standing still on the ground. She's our inertial frame. She watches Bob's car accelerate, and she can easily calculate that the engine's force is causing that acceleration. For her, F equals ma works perfectly. But now let's jump into Bob's perspective, from inside the accelerating car. From his point of view, it looks like Alice is the one accelerating, backwards. And there's no force pushing her. From his non-inertial frame, F equals ma completely falls apart. The first law is that crucial rule that tells us, hey, you have to be in Alice's frame for the physics to make any sense. Okay, so the first law gives us the rulebook for where physics works. Now, let's see what happens when we actually use that rulebook and apply the second law, F equals ma, to the real world. Honestly, its power is absolutely staggering. Get a load of this number, 98.04%. That is the accuracy scientists were able to achieve using just motion capture data and Newton's second law to predict the incredibly complex forces between an athlete's foot and the ground in real time. I mean, think about that. That is a stunning, almost unbelievable level of predictive power from a 300-year-old equation. And you see its application in sports and biomechanics absolutely everywhere. We're talking about everything from calculating the perfect forces to optimize a hammer throw to making sports like soccer safer by analyzing the forces on a player's head, and even developing training that helps reverse age-related muscle decline. The second law is a true workhorse for human performance, and F equals ma helps us make really specific, practical decisions. For instance, when researchers used it to compare pneumatic resistance, like those air pressure machines at the gym, to old-school free weights, they found some clear differences. The law showed that pneumatic training is way better for generating speed and power with lighter loads, while free weights are still king for building pure, maximum strength with heavy loads. It lets us tailor training to get exactly the results we want. All right, so that brings us to the famous third law. Now, it's often quoted all by itself, but its real magic, its true power, is only revealed when you see how it connects perfectly with the other two. For every action, there is an equal and opposite reaction. Simple, right? When one body pushes on another, that second body pushes back with the exact same amount of force. It's so elegant, and it's the key that unlocks one of the most fundamental, sacred principles in all of physics. And here's where it all snaps together. The third law tells us the forces are equal and opposite.
The second law tells us that force is the thing that changes momentum. So if you put those two ideas together for an isolated system, the math works out beautifully. Any momentum gained by one object must be lost by the other. The total momentum of the whole system never changes. And boom, that's the law of conservation of momentum, a direct consequence of Newton's second and third laws working in perfect harmony.
So let's bring this all full circle. We started with a simple mistranslation, and now we can see how all three laws beautifully interconnect. They don't describe a universe where things are left alone. They describe a universe governed by the constant, never-ending interplay of forces. And hey, if you have any doubt left about that insofar as interpretation, just look at Newton's own example for his first law. He didn't pick some rock floating in the void of deep space. He chose a spinning top, an object that is very clearly being acted upon by the forces of gravity and air resistance. He used it to show how its motion changes insofar as those forces act on it. It was never about a force-free world. This is the real powerful message of Newton's first law. It's not some abstract thought experiment. It is a universal principle of cause and effect. It tells us that for every single change in motion we see, every jolt, dip, swerve, and spurt, we should be looking for a force behind it. So the next time you're just sitting still or walking down the street, or even just turning a corner in your car, think about it. Newton's laws aren't just concepts in a textbook. They are an active, real-time description of the constant push and pull of the universe on you. The real question the first law is asking us is this: what unseen forces are changing your motion right at this very second?